All right. Good afternoon, everyone. Thank you for joining us here at Lisbon. This is Gero. He's the technical marketing lead for Murata. My name is Oriol Chavanel. I'm the ecosystem tech lead for an OCP lead for Submer. And together we're going to present to you what we have been doing this last year on the advancements about integrating power delivery in immersion. So you will see a wide summary of what we have been testing and moving forward, about the limitations, advantages that we can find by delivering Open Rack version 3 in immersion. So not only air-based racks, but the integration within immersion tanks. So as a quick summary, everyone, we know how the density of the things are moving forward, how quick we are going into more density, more demand, IT demand for CPU, GPU, and so on. So people usually only think that this is affecting only the IT side of the things, but of course data centers have other concerns, cooling concerns, electrical concerns. And when we go about electricity, we see other things which are never considered, like connectors, like cables, like how we are going to turn from DC to AC or AC to DC, voltages, and so on. So this is what we are working in this work stream. For example, this is one of the focuses that now has industry about the TDPs that are coming up with different GPU and GPU processors that we are tackling in industry in different ways with increasing TDP and so on. But, of course, everyone, as I say, is focusing on where the air is finishing, like 300 watts, 400 watts, and how we are going to tackle this with the liquid cooling, different technologies in the world. But, of course, no one is thinking on, well, what about the power, right? How we are going to deliver the 8 kilowatts, 9 kilowatts PSUs that we hear that they will come up with AI and so on the upcoming trends. So we really believe that immersion is maybe the better driver to cope with all of the components that are getting hotter in immersion. So you don't need to probably rely on other technologies that are focusing the cooling of those component by component, tackling every one of those individually, which probably is not very easy to scale up in the upcoming future. So basically, what we have been doing in the work stream is to define which are the verticals that we are tackling here, right? So in an immersion tank, you will find, speaking about power, the busbar, which is sitting in the bottom of the tank. You will have, of course, the power shelf, which is delivering the power. And then you have, of course, the servers, which are delivering the compute later on. All of that is cooled down by a CDU, a cooling distribution unit. So we have been also deciding and speaking open where every component might have more sense to be installed, how all of these can collide together. So for example, as you can see there, the bus bars are in the bottom seating, but they are in a zone that typically the fluid is being pumped. So it's where the fluid is more cold. So from the bottom to the top, we have this forced convection that we are pumping through the tank. And then you have, of course, all of the different servers and power shelves actually differently integrated in the tank. They don't have a specific necessity to be in one place or the other one. But, well, you will see now the data that we have been testing recently and how far we can go in immersion comparing to the limitations that air has now at the moment. So as a summary of the different testing materials that we will come up now, we have the first part, the power shelf design and densities. The testing that we have been doing is about a power shelf of 54 kilowatts, so at maximum capacity. Then we also have been testing the busbar, a current ORV3 busbar that was designed for air. We just checked material compatibilities and other things to be adapted for immersion. And we brought 1,000 amps to that busbar to see which was the temperature increase for it. The same with connector design. So we had the team of Molex that unfortunately cannot make it here, but they have been doing a lot of good testing as well to understand how many amps you can bring into a connector that was designed for air, but in immersion you can do it like twice or 3 times the same pumps because it's in a very cool, well-cooled environment, sorry. The same with material compatibilities, a lot of work that Amy, Peter, and the Material and Fluids group has been doing, but also we have been checking further to understand the jacket of the cables, the connectors, thermoretractile materials that can be used for separating power, negative and positive into the cables. And finally, also the increase that you probably everyone know about using a higher voltage that can also help reducing the temperature of the materials. So just to get on track, sorry for the long intro, if you want Kevin to speak maybe about the power shelf design.
So what we've done here is we've taken the standard power supplies and we've modified them by stopping the fans, removing the fans, and making sure the material compatibility is there inside. Making sure we don't have any materials that are going to cause problems. Basically, we don't have any materials that are causing problems to date. We keep looking and keep checking because, you know, we're not used to this. So we're figuring it out as we go, but we're so far so good. We then decided we're going to put the incoming AC power out of the fluid. A couple reasons for that is we want to use standard AC cables. You don't have to seal the cables. They're much less expensive. It just made sense for us to do so. Also, the operator doesn't have to put his hands in the fluid. The other thing we did is the controller is in that same location. Again, so you don't have to put your hands in the fluid when you're putting things together or you take them out, that sort of thing. Then we put 15 power supplies to produce 54 kilowatts. And it's in a 3OU space. So now all of a sudden you've got 54 kilowatts in that space, which is pretty nice from a power standpoint. So that's what we've done. The other thing we had to do is make sure that they're in groups of 3 so that you have a balance, so that when you have a Y configuration, you don't have major neutral currents. You have no neutral currents. So all the power supplies, they share, they have the same voltage, they produce the same currents, so everything works copacetically. Okay. Then the other thing that happened here is we finished our testing. We put the product into the tank, and we put 54 kilowatts on it. And what we did is we compared what an air-cooled system at 54 kilowatts would show up compared to our immersion fluid design. And what we found was that as you look through here, you don't see any temperature above 70 C. But if you look on the left-hand side, you see what my temperatures were under normal operation in air. 150 C, 175 C, 150 C. I don't have a temperature in fluid above 70 C. Guess what? Everything's working very, very nicely. In fact, my next step is to take that same power supply in fluid, remove the overcurrent protection, and start ratcheting up the amount of power. See how much power we can get out of this power supply and keeping the thermals the same. Now, of course, I have to take into account the fact that I have certain components and I don't want to exceed their normal current ratings. But as you can see, I've got 60, 70 degrees delta between air operation and fluid operation. So anyway, it's a very good picture from the power supply. One thing that I will say is that this shows you something, that putting a power supply into immersion really does work very well. Then again, the power supply is only dissipating 5%, 4%. So we're not dealing with a lot of power. Again, this is just showing the different power levels in each one of the power supplies. And as you can see, they're very, very close to each other, which makes sense because that's what we're trying to do. We're trying to force each one of the power supplies to have the same voltage, to produce the same current, so that way everybody's sharing. And that's the whole approach with this type of design. And they do. As you can see here, the outputs are very, very similar. So it did exactly what it's designed to do. Okay.
Thanks, Kevin. Just to add, this also has been in the worst case possible scenario. So the testing was concurred at 55 Celsius fluid inside the tank, typically temperatures that we are already starting to use for heat reuse. So having these voltages very stable, the kilowatts delivery just perfectly working fine. As Kevin was saying, no component going farther than 70 Celsius, while in air they are at 140, 150, is indeed a very good environment that doesn't need an over-design for the upcoming trends, upcoming densities, just a bit of adaptation to keep everything working in immersion. I'm going to jump on the power advancements for the busbar. So with the busbars, we have done the same. As I was saying before, this is an immersion busbar, but at the end, it had no other modification than what we will say how to hang it in the bottom of the tank with the screws, so different positions just to tie it in the bottom of the tank. But the rest is actually something that you will find in air. Even though these small vents that we are just referring here, those are present in air, but they are very helpful because they are even helping the fluid to go through and keep a very good temperature. So the testing that we had made here, it's again showing, by the way, this is down here at the right, the testing pot, sorry. So there is the power shelf that Kevin was commenting at the left. There is the load, dummy loads at the right, generating the proper load to consume that 54 kilowatts. Of course, we have not done it with real servers because it's very expensive if something goes wrong. So in the busbar up there, we have put all of these thermocouples to read the temperatures in the different parts of the busbar and understand what was going to happen. So what happened is that in immersion, bringing 1,000 amps of load, so 50 kilowatts, was not even increasing 5 Celsius of temperature in the same ambient. While in air, you can see the trend in the red line, so probably just by 1,000 amps, we are already on a 35 Celsius increment of temperature, so probably on a solutions, as I guess Meta was presenting this morning, going on a higher and higher busbars with more copper to reduce the temperature that we are having in air environments. So here you can see what I was just saying now. So what is the roadmap for a busbar, ORV3 busbar at the moment in air, in liquid? So the current ORV3 busbar, which is down here in the right, normally with air copper, and how big is becoming, at the right with HPR, which is a bigger version to cope with all of these densities. So again, is another scenario where we can see that in immersion, we don't need to go for over-engineering every component, everything. The things just can work as they are with small adaptations of materials and probably hanging systems. Now going to the connectors, it's the graphics are very similar to each other, but trust me, they are on a very different testing environments, each of them. So this was carried out by Molex, as I was commenting before, and they have seen that the connector, again, it's suffering the same type of trend. Like in air, you are bringing to a power shelf connector delivery, so 400, 450 amps, and we're going to an increase of 50 Celsius, which is a lot. In immersion, we are seeing the blue line, which is in 100 amps, we are going on 20, 25, which in the bottom of a tank in immersion, it's of course more than high to have. The same with the connector for the servers this time, similar lines, similar situation. So we are seeing in all of the power elements that are in immersion the same thing. Again, we can work out everyone with the server vendor industry how to tackle the chips like GPUs, CPUs, other problems that are creating very concrete heat points with convected flow, directed flow, precision cooling if required, but the rest of elements which are starting to become more hot, they can still be in immersion, very well cooled down, so there is no need to over-engineer the rest of the elements so far. Here is a bit of what probably already Amy and Peter explained, and we'll go very fast on that, but is the compatible materials that we have been testing on the cables and connectors, so something that also the Molex team and others have carried out at their site, which cables we can use, which thermocouple, I don't have now the word in English, sorry, but is this material that you use to connect both the connector with the cables, that with a bit of heat you can adapt it, so it's working very nice. So this is a bit of the study that you have been doing, at which temperatures, up to 85 Celsius, very well to work in immersion, of course. So this is a bit more of their information. For example, the weight change is the cables are absorbing fluid. Are they increasing? Are they stiffening? Are they changing the dimension, the color? All of that is that we have been testing out with a really good result, actually. So POR, it's one of the our best probably element that we recommend typically for immersion, and also the SOOW. It's a specification still, but it's also a very good friend for power and cables jacketing in immersion. So I'm going to now hand over again to Kevin to speak about the voltage increases.
So even though everything looks beautiful, everything looks fantastic, we've got one of my pet peeves. You still have a thermal rise in the connectors. You still have a thermal rise in the bus bar. So if we take the standard ORV3 voltage of 50 volts, 51 volts, and you look at that versus if you use 54 volts, which most servers can easily handle if we talk to the server manufacturers and you use a DC to DC that allows it. The difference between 51 volts and 54 volts at 50 kilowatts is a 10.8% difference in the voltage drop in a given resistance. So what happens, that directly relationship to the thermal rise. So it's almost 11% difference just by running it at 54 volts. Now, in the previous past, air-cooled racks did 10, 12 kilowatts. It wasn't a big deal. So they went to the 51 volts. That's one of the reasons they did it, because inside the server, they can use a non-isolated DC to DC. If you went to a 54 volts, you still could use a non-isolated DC to DC, but the efficiency would be a little bit less. But you can see here, in these devices that are going to be pushed, the bus bar and the connector, by going to 54 volts, it's almost 11% difference in the thermal rise, or in the voltage drop, which is directly relationship to the two. Anyway, that's one of my pet peeves. If you talk to your server vendors, if they can do a 54 volt, I think all of us are going to be happier if we're trying to do 50, 75, 150 kilowatts, which is what we're coming to. Anyway, thank you very much. If you want to join us, please do so. We have a very, very lively discussion most days. We open it up. We love to hear from people, especially people that have different opinions, because guess what? It makes us think, it makes us learn, and it really works very well. The other thing, too, I will say is that we're starting to collaborate more. You may have seen how we're changing our structure a little bit. We're putting everybody together, and we're able to go between groups and gain the experiences and the knowledge from each one of the different groups, and we're trying to do that readily. So thank you very much.